This is the presentation video for restoring degraded old films with recursive recurrent transformer networks. First, let's talk about the background of our study. As we know, films degrade over time if it was not properly preserved. Typical forms of degradation include scratches, dust, dirt, and color fading. Before digitization, some contaminants can be physically removed from the film. Nevertheless, a significant amount of noise remains which cannot be easily removed and must be processed digitally. In the past, restoring these degraded old films required experts to manually process each frame, making this task both labor-intensive and time-consuming. With technological advancements, some deep learning-based methods have been developed which can be used for the restoration of old films. However, complete removal of difficult film noise is still a challenge. These examples demonstrate the restoration of old films using the existing approaches. Although most of the film noise has been removed, there remains some noise that has not been completely eliminated. Here are contributions of our work. We've developed a method for explicitly modeling film noise masks, and with advanced propagation, alignment techniques, our method has ability to remove more challenging film noise. Additionally, we introduced an adaptive recursive architecture which can improve temporal coherence, significantly reducing flickering and other film damage. Moreover, we conducted in-depth comparisons with existing approaches that demonstrate the effectiveness of our approach. Now, let's dive into our proposed method. Here's an overview of our network. There are 3 important parts of our network, and I'm going to go through each of them in the following slides. The first part is Film Noise Mask Estimator. It aids in estimating the film noise mask, which acts as a hint for subsequent restoration processes. In calculating the mask of the current frame, the estimator computes the variances between the current frame and the warped adjacent frames. The final mask is then derived by calculating the geometric mean of these variances. The goal of this part is to maximize the use of features in different time and depth to perform restoration at the feature level. The features are propagated and aligned using the second-order grid propagation and flow-guided deformable alignment methods proposed in basic VSR++. Then Swin transformer is used to restore and fuse the aligned features. Finally, to remove film noise that is not completely removed, a recursive architecture is introduced. If the film contains noise that is difficult to remove, then the number of recursions will increase. The recursion ends when the mean squared error between yt and xt falls below a threshold epsilon, which is set to 10 to the power of -4 in our experiments. This can be interpreted as stopping the recursive process when the model's adjustments to the video become minimal. 2 pre-trained parameter sets θ1 and θ2 is used during difference recursion steps in inference stage. In the first recursion, the first parameter set, θ1, is used for overall image quality enhancement. In subsequent recursions, the second parameter set, θ2, is used for further noise reduction. We conducted experiments to verify the effectiveness of our proposed method. This page lists some details of the experiments. We used synthetic and real degraded films to train and test our model. Since no ground truth data exists for real degraded films, it is necessary to create synthetic degraded films from ground truth for model training. For training, the synthetic degraded films are synthesized based on the REDS dataset, whereas for the test set, They are synthesized from the Davis dataset, and real degraded films are collected from the Internet. In qualitative evaluation, we use real degraded film to assess model performance. As for the metrics, we use PSNR as SIM-LPIPs for synthetic degraded films, and for real degraded films we use no reference metrics BRIS and NITE. As a result, our proposed method performed best on all metrics. The comparison video shows that the proposed method can effectively remove film noise that cannot be completely removed by other methods. The ablation study showed that B noise mask and C propagation and alignment contributed to the performance improvement. However, the incorporation of the recursive architecture in isolation appeared to have a detrimental effect. This suggests that without the foundational accuracy provided by other components, errors in the output frames may be amplified after multiple recursions. The best result is obtained by combining all the components. In conclusion, we proposed a framework called Recursive Recurrent Transformer Network for degraded old film restoration. Through experiments, we verified that the proposed framework outperforms existing approaches and is effective in removing complex film noise. As future works, our method still has two weaknesses. First, due to the greater complexity of the proposed method, the time required for inference is longer than for other methods. In particular, as the number of recursions increases, the execution time also increases linearly. Second, as shown in these two images, there is a problem that non-noise elements, such as smoke, are misidentified as noise and removed. Reducing misidentification like this will be an important future work. That's all for the presentation video. Thank you for watching.